Hey guys, over the summer, when you're flying off for your vacations, don't just put on your headphones and zone out on the plane. Instead, start a conversation with the person next to you about how in the world you're flying 9,100 meters in the air in a 394,000 kilogram metal tube. After this video, you can tell them it's because of lift. Lift is pretty cool, and it's based on Bernoulli's principle, something we learned a lot about during the year. Just a refresher on Bernoulli's principle, it states that fluids moving at a higher velocity exert lower pressure on surfaces than fluids moving at a lower velocity. Now, I know some of you are thinking, but William, air is not a fluid. Actually, in most cases with fluid dynamics, air is considered a fluid, and therefore its kinetic energy is given as 1/2 of rho, the density, times the velocity squared. The pressure imbalance required for Bernoulli's principle to actually take effect is caused by the airfoil shape of wings. The shape of wings is a large reason why Bernoulli's principle takes effect. Air is allowed to pass smoothly over the top of the wing while it comes straight on, but while it goes under the wing, it is stopped because it keeps on hitting the wing itself. Therefore, the air on top goes much faster than the air on the bottom, creating a pressure difference and, therefore, lift. But now you're probably asking, but William, the Wright brothers who flew the first plane, had pretty much flat wings on their plane. How on earth could they achieve any lift? Well, also, a Newtonian definition of lift applies, where, since this wing exerts a downward force on the air also exerts an upward force on the wing. So, by changing the angle of attack of this flat wing, the air then comes at it from this direction, creating a downward force on the air and an upward force on the wing itself. These two sources of lift account for the many different shapes and types of wings used to create lift. There are two possible ways to increase lift on a plane. The first would be to increase the angle of attack. The angle of attack is the angle the plane makes with the ground. By increasing the angle of attack, you increase the amount of air that hits the underside of the wing and deflects down, thus increasing the Newtonian force of lift. The second way to increase lift is to increase velocity. By increasing velocity, you change the amount of air that moves over your wings per second. Therefore, the Bernoulli portion of lift is increased because the pressure difference is greater. Now let's shift our focus back to the plane. Lift, which is a force, obviously needs to exceed or equal the weight of the plane for it to get anywhere. So let's take a look back at our commercial airliner. First, the equation without numbers. Lift is equal to the coefficient of lift times the kinetic energy of the air times the area of the wing. Since the force of lift has to oppose the weight, let's set lift equal to the weight to find minimum velocity. Here we have the coefficient of lift found from a graph, multiplied by the density of the air times the velocity squared over 2, multiplied by the area of the wings. After some calculations, we can come to the conclusion that the velocity must be around 796 kilometers per hour. So now you say, cool, I know how fast my 747 has to fly to stay in the air. But why else should I care about lift? What does it really matter? Well, here are a few things that also need lift to function. Flying squirrels create lift more with the Newtonian definition by deflecting air downwards with their wing flaps. Car manufacturers have to take into account lift so that their cars don't lift off the ground. Much like flying squirrels, kites and sails create lift by pushing air downwards or away from the direction of movement in order to get an equal and opposite force pushed back into them. As you can see, a lot of things require lift to work, but the main thing is airplanes, and that's what matters the most to us right now. So, here's a model F-22 that belongs to my little brother. It weighs about 0.2 pounds, so let's see how fast it would have to go to get off the ground and stay off the ground. Utilizing this graph, and let's say our angle of attack is 8 degrees, we can see that our coefficient of lift will be 0.8. Again, let's start with our equation without numbers. For this one, we're going to have to switch over to imperial units. We have the 0.2 pounds of lift is equal to the 0.8 coefficient of lift times the density of air at sea level times the velocity squared over 2 times the surface area of the wings of a 1,000 or 1 to 100 scale aircraft. By solving for velocity by isolating v, like last time, we can figure out that with an angle of attack of 8 degrees, this plane only needs to go 51.1778 miles per hour at sea level to achieve minimum lift. Now that we've looked at a few things that use lift and how we can apply lift, let's go back over what we know about it. First of all, lift is calculated with this formula. First of all, we have the coefficient of lift, which is found usually experimentally and is listed on tables if you want to know. Then we multiply by the kinetic energy of the fluid the plane is moving in. So for this, it would be rho v squared over 2, which is the kinetic energy of the air, times the surface area of the wing. So that means that there are two ways to increase lift on a pre-existing aircraft. That would be by going faster, increasing your velocity with relation to the fluid, or changing your angle of attack, which would change your coefficient of lift, which was shown in the graph. Also, there are many different kinds of wings which create lift. So, here are two examples. The first is the typical airfoil shape, which utilizes both forms of forces that create lift. The Bernoulli pressure difference, where this air goes faster than this air, creating more pressure on the bottom of the wing where there is slower moving fluid. Or this one, which, when the angle of attack is changed, more lift is created because more air is hitting the bottom here. That's the same kind of lift used in kites and flying squirrels. So, now instead of putting in your headphones, playing Flappy Bird, and listening to Party in the USA on repeat for 3 hours of your flight, you can enlighten your seatmate on Bernoulli, Newton, and how the Wright brothers invented a plane, which is why you are both now sitting 30,000 feet above sea level in an aluminum can that just so happens to fly with lift.